At first glance, this next problem looks great because it's set up for us. We've got the limits of integration. We don't have to worry about the setup. We can go straight to integration. So all we have to do is find an antiderivative of e to the x squared with respect to x. On second glance, it doesn't look so nice because I do not know of a nice formula for e to the x squared with respect to x. This is not, by the way, this is, if you see e to the x squared, that's not the same thing as e to the x squared. Now that would be simple because that's just e to the 2x. This is e to the x squared. It's not necessary to draw in those parentheses, but if you're at all likely to read that wrong, you might want to do that. Okay. It can actually be shown that there's no really nice formula that we can write out with our usual friendly functions for an antiderivative for e to the x squared. So I don't want to integrate with respect to x. But I'd be perfectly happy to integrate this function with respect to y, because with respect to y, that's a constant, and I just get y times that. So I want to Fubiniize. I want to switch the limits of integration, so I can do my y first and then my x. Now when we do that over a rectangular region, it's nothing. You switch these, you switch these. But if I switch these limits of integration, I've broken my rule. Functions inside, numbers outside. I can't Fubiniize by just switching things around. That's not to say I can't Fubiniize. I can, but what I have to do is figure out what is this region that I'm integrating over, and then how can I describe it the other way. So, I'm going to draw a picture of my region. I can see my y values are going from 0 to 3. So y equals 0 is the x-axis, that's my bottom boundary. Y equals 3 would be a horizontal line at height 3. So my region has these two horizontal lines as the bottom and the top boundaries. My left boundary is x equals y over 3. Now, I'm not super used to having x as a function of y, so I'm just going to rearrange this to y equals 3x. Oh, okay, that's fine. That's a line of slope 3 through the origin. So I'd come through the origin, up 3 over 1. That's my left boundary. And my right boundary is x equals 1. X equals 1 would just be a vertical line. Now notice that's going to pass through this point because we just got here by coming up 3 over 1. So x equals 1 is my left boundary. Now you might have been tempted, once we had these two horizontal lines and this line, to think that this was the region over which we were integrating. But you assumed if you did that that the y-axis was one of your boundaries. I don't see x equals 0 as one of my limits of integration. So the x-axis, while it's drawn as part of the picture, does not count as a boundary. It might actually be helpful to just draw in my boundaries using a different color. Then, by the time I've got those three boundaries, I can say that doesn't fully enclose a region. I need my fourth boundary. And then I can see the only region that's fully enclosed there is this triangle right here. So that's the region over which we're integrating. And these limits of integration were set up so that we were essentially slicing things horizontally. So that when we calculated our cross-sectional area, we were integrating from left to right. If I want to switch my limits of integration, I want to set it up so that I'm slicing things vertically instead. Okay. So I can say now the bottom is y equals 0. The top is y equals 3x. Bottom and top, now I've got y as a function of x. One of them's constant, but one of them's not. Okay. X equals 1 is my right boundary, and I can see then my left boundary is x equals 0. That's where the floor and the ceiling actually meet. So that entire line isn't part of the boundary, but just this point will be. That's where my slices start if I'm slicing this way. So then I can say this is the double integral. The inside integral is now going to be the one with respect to y. So we're going from 0 to 3x e to the x squared dy. And then we're integrating from 0, where the slices start, to 1, where the slices end, with respect to x. So you'll notice I'm now integrating dy dx instead of dx dy. But I did not get there by simply switching the limits of integration that I had. I now have functions of x on the inside and constants that are constant y values on the outside. Okay. So when you're switching things, you're describing the same region, but don't make the mistake of thinking that you can just switch these, or that you can somehow work with it one at a time. Say, what do these guys become and what do these guys become? Because it doesn't work that way. Because here, this was saying that the left side was x equals y over 3. But when I'm slicing things this way, I say the left boundary is x equals 0. Because now I'm not looking for what's the left side boundary of a slice. I'm saying what's the left boundary of the entire region. So whatever's on the inside, you're looking just at the slice. It goes from what to what. What's on the outside, you're looking at the entire shape. And so you have to basically draw a picture in order to switch the limits of integration. All right, once we've done that, we can at least do the first integral. Because that's constant with respect to y. So we're going to get the integral from 0 to 1, y e to the x squared, evaluated between 3x and 0, and then we integrate that with respect to x. So that's going to be the integral from 0 to 1 of 3x times e to the x squared minus 0 times e to the x squared dx. That's nice. Now I don't have e to the x squared by itself. I'm multiplying by an x. I'm going to be able to do a u sub. Oh, math is so cool. Okay, so I'm going to just pull that 3 outside and say that's 3 copies of the integral from 0 to 1, x e to the x squared dx. Let's let u equal x squared. Then du is 2x dx. Now I've got the x I need. I'm going to introduce a 2 counterbalanced with a 1/2 on the outside. And so this becomes 3/2. The integral from the u value at 0 will be 0 squared, which happens to still be 0. And the u value at 1 will be 1 squared, which happens to still be 1. And then we just get e to the u du. So that's going to be 3/2 e to the u evaluated between 1 and 0. And so that's going to be 3/2 times e to the first is just e minus e to the 0 is 1. And you can keep that 3/2 factored out, or you could distribute it 3/2 e minus 3/2. Either version of the answer is fine. But you'll notice I often write when I plug in 0 and I happen to get 0, I still write that I'm subtracting that. That's because I know there are times like this where when I plug in 0, I don't get 0, I do get something to subtract. So I'm sort of in the habit of very often, not always, but very often I'll write down that I'm subtracting what I get at my lower limit of integration, just so I don't forget that important step.